Good morning. Today we're going over our second homework assignment for acids and bases. And this one is going to go over a lot of calculations for pH and titrations and buffers, and it's going to pull in a lot of the stuff that we've been doing throughout the whole semester. This is like our capstone chapter, so it should be a good time. It might be a little bit challenging, but I hope that you guys recognize what we're doing as an extension of things that we've already been doing and get excited about all of the steps that you know how to do and all of the chemistry that you are understanding at this point. All right, so the first thing we're going to do is talk about the pH scale. And the pH scale is a way to measure acidity. And we've got these two equations here. We find that the pH is equal to the minus log of the H3O plus concentration. And we did a little bit with H3O plus concentrations on our last homework assignment. And the inverse of the log is base 10 exponential system. And so if we have the H3O plus, we want to find the pH, we can plug it in here. But if we have the pH and we want to find the H3O plus, we go backwards and find that the H3O plus concentration, this brackets means concentration, which is in units of molarity, by the way, that's going to be 10 raised to the negative pH. So if I know the pH, I can plug it in and find the H3O plus concentration. And if I know the H3O plus concentration, I plug it in here, and that'll give me the pH. And both of these equations are given to you on an exam. And for the pH scale, we see it goes, generally speaking, from 1 to 14, although it can go a little bit less than 1, a little bit more than 14. But for the moment, we're going to say from about 1 to 14. And at 7 is neutral. Neutral. And if we're less than 7, we're acidic. Less than 7. If we're greater than 7, we are basic. All right. So first thing first, they say, what's the pH of an aqueous solution if my H3O plus is 2 times 10 to the negative 14th? We're just going to plug it in here. If I know my H3O plus, I can find my pH. And we have to get the negative log of 2 times 10 to the negative 14th. Every one of you is going to have a different calculator that does this slightly differently, but what this particular calculator is going to want is to say 2 times 10. It's going to say 2 times 10 to the negative 14th, and I'm going to take the log of that. So click log. And then I'm going to take the negative of that. So I actually have a pH of 13.7. Next, we've got carbonated cola, more acidic than coffee or even orange juice. What is the H3O plus if my pH is 3.120? And again, now I know the pH, and now they want the H3O plus. So I'm going to use this equation. 10 to the negative pH is going to give me the H3O plus. But I can't just put 10 raised to the negative 3.120. Okay, I can't just put that in because that's a nonsensical answer. We only use scientific notation if these are whole numbers. So I actually have to convert that to a regular whole number scientific notation thing here. And your calculator, again, is going to be different than mine. Yours might have a little hat or a x to the y button. I could use x to the y. I could use 10 to the x. Let's try the 10 to the x. If I put 3.12, I'm saying that's x. And if I click on 10 to the x, then I'm saying 10 raised to this thing. And that gives me a concentration of 7.58 times 10 to the minus 4th. See how that exponent here for scientific notation has to be a whole number. Just to show you another way of doing it, I could use the x to the y button, and I could say 10 is x, and then x to the y, it's giving me that little caret or hat. And then I'm going to say 3.12 negative, that's y. And then click equals, I get the same answer. So whether I use the 10 to the x or the x to the y button, or if you have a little caret button, you should practice doing this to make sure you're getting the same answer. That will ensure that you know how to use your calculator when you're at the test, and that's the important part. Okay, next part C, we're going to rank these from most to least acidic. And in order to do that, then we're going to follow this scale. So the lower I am, the more acidic I am, and the higher the number, the more basic I am. So we know that pH 3 is more acidic than pH 5, and pH 5 is more acidic than pH 14. So this currently is going from most acidic to least acidic, and then these two we might want to plug in to see exactly what it needs to be. So the minus log of this H3O plus, we're going to say if I have 10 raised to the negative 6th, if I have 10 raised to the negative 6th, that is 1 times 10 to the negative 6th, and I take the minus log of that, then I'm going to take the log, and then the negative of that, and I get a pH of 6. So this is going to go right there. And for my other one, if I've got 1 times 10 to the negative 2, 1 times 10 to the negative 2, I take the log of that and the negative of that log. That gives me a pH of 2. That's more acidic than my pH of 3. So I had to convert all of those to the same scale, the same pH scale, so that I could actually answer that question reasonably. Now we're looking acidic, basic, or neutral, and we're just going to say a less than 7 is acidic, greater than 7 basic. So saliva is less than 7, it's a little bit acidic. Urine is even lower than that, so it is also acidic. Pancreatic juice is greater than 7, so it's basic. Bile, basic. And blood, slightly basic, but still greater than 7. Here I've got a solution of borax and human saliva. Got both of those together. Got two different solutions. So the more acidic one is saliva because it has a lower pH. So saliva, solution B, is more acidic. What is the H3O plus? I'm just going to plug it into this exact same equation that I've got. My H3O plus is 10 to the negative pH. So my pH is 9.2. Then 10 raised to that is 6.3 times 10 to the negative 10th. Right? Same thing for solution B. H3O plus is 10 raised to the negative pH, or 10 raised to the negative 7.1. Which is 7.94 times 10 to the negative 8th. These aren't terribly difficult questions, except that you do need to know which equation to use when. So look at what you're given, pH, look at what they're asking for, H3O plus, and look for a convenient equation that says, let me solve for H3O plus if I have the pH. Now, what is the hydroxide concentration in solution A? Well, it will help us to remember from our last homework assignment that the H plus, or the H3O plus, multiplied by the OH minus was 1 times 10 to the negative 14th. It's the reason that pH scale goes up to 14. Okay, sorry. Equals 1 times 10 to the negative 14th. So if I know the H3O plus, I can solve for the hydroxide. 1 times 10 to the negative 14th divided by the H3O plus. So the hydroxide concentration of solution A, if this is my H3O plus, then what I need is 1 times 10 to the negative 14th, 1 times 10 to the negative 14th, divided by my H3O plus concentration, which is 6 times 10 to the negative 10. 6 times 10 to the negative 10. That gives me 1.7 times 10 to the minus 4th. excuse me, let's try that again. We're going to take 1 times 10 to the negative 14th, and I'm going to divide it by 6.3 times 10 to the negative 10. So 1 times 10 to the negative 14th divided by 6.3 times 10 to the negative 10th. That gives me 1.6 times 10 to the minus 5th. Okay, they're kind of called that a rounding issue. 1.58, see what they say. They want the hydroxide concentration using 1 significant figure. So round that up to 2 times 10 to the negative 5th. I feel like I'm losing a lot of information there, but okay. And next, again, 1 significant figure. Gonna have to look out for that. Hydroxide solution for solution B. I'm going to say 1 times 10 to the negative 14th divided by now 8 times 10 to the negative 8th. Gives me a hydroxide concentration of 1 times 10 to the minus 7th. There we go. Now going back the other direction, we can, if we're given hydroxide, we can calculate H3O plus, and it looks like this. Of course, coming from here, my H3O plus equals 1 times 10 to the negative 14th divided by my hydroxide. And once I have my H3O plus, I can take the minus log to find the pH. So 1 times 10 to the negative 14th divided by 3 times 10 to the negative 7th gives me a H3O plus concentration of 3.33 times 10 to the negative 8th. Plug it in here, take the log of that, take the negative of the log, and I get a pH of 7.477. They want 2 decimal places, so let's say 7.5. That's all right. So the next one, we've got an H3O plus of 4.7 times 10 to the minus 3. That one's really nice because I don't have to do an extra conversion. I can just plug it in right here. Take the log, take the negative, and I get 2.3. Again, if I'm given the H3O plus, I just plug this in. I've got 1 times 10 to the negative 4th, and I take the log of that, and I take the negative of the log, and I get a pH of 4. And finally, another one here where I'm given the hydroxide concentration. So I have to take that extra step of 1 times 10 to the negative 14th, divide that by the hydroxide, 9.2 times 10 to the negative 9th. That gives me my H3O plus concentration. And then I can plug that into this top equation and say the log of that, the negative of that log, gives me a pH of 6.0. All right, and then going backwards here, if they give me pH, can I calculate H3O plus? Can I calculate hydroxide? And again, this is what I'm going to be using at this point. I plug the pH in here, I can find the H3O plus. And if I have the H3O plus, then I can plug that in here to find the hydroxide. So let's have a look at that. 10 raised to the negative 3 I'm going to say -3. 10 raised to that gives me an H3O plus of 0.001. And if this is my H3O plus, then 1 times 10 to the -14th divided by that, 0.001, gives me my hydroxide concentration, which is 1 times 10 to the -11th. Next, if my pH is 6.46, then 6.46 negative, 10 raised to that gives me my H3O plus, using that equation. So that's 3.5 times 10 to the -7th. And if I want to know my hydroxide, I've got to take 1 times 10 to the -14th, divide by that. So I'm going to store that, and I'm going to say 1 times 10 to the -14th divided by 3.5 times 10 to the -7th. I just recalled that thing I stored. That allows me to keep all my all my digits, whether they're significant or not, and then I can round at the end. That's always the best idea, to round at the very end. That gives me 2.9 times 10 to the -8th. Now, if my pH is 8.7, 10 to the -8.7, gives me a H3O plus concentration of 1.99, or 2.0 times 10 to the -9th. And then I'm going to store that to memory, and then say 1 times 10 to the -14th divided by that value, 1.99 times 10 to the -9th. That's going to give me my hydroxide concentration of 5.0 times 10 to the -6th. And last one here, if my pH is 11.15, then my H3O plus concentration is 10 raised to the -11.15. That is 7.1 times 10 to the -12th. And my hydroxide concentration is going to be 1 times 10 to the -14th divided by this value. So I'm going to store that and then say 1 times 10 to the -14th divided by that value, 7.1 times 10 to the -12th, gives me a value of 1.4 times 10 to the -3rd. There we go. Now, what is the pH of a solution prepared by dissolving this much HCl in this much solution? So the first thing we recognize is that HCl is one of our strong acids. That's important because that means that this reaction goes essentially to completion. I get H plus that separates completely from the chloride. Now, if I'm in water, which of course I am in water, then it might be more appropriate to say this dissociates in water to form H3O plus and the chloride. And what we're interested in is this, because that's what we're going to use to calculate pH. Now I know that if I've got 1 mole of this and it dissociates completely, then I have 1 mole of this. There's a 1-to-1 molar ratio, and that's important to answer the question that they are asking here. So let's clear up some space. And the first thing we need to do is say, well, if I need pH, pH equals minus log of the H plus, or the H3O plus. If I need H3O plus concentration, then I need, concentration is units of moles per liter. So I need moles of H3O plus divided by liters of solution. That's what I need to get molarity. So I have the concentration, which I can plug into this equation. So if I'm starting with 7.5 grams of HCl, Then I've got grams of one thing, I need moles of another. I need to do stoichiometry, follow my roadmap. Tells me if I want to go from grams of one thing to moles of another, then the first thing I need to do is go from grams of one thing to moles of that one thing using the molar masses on the periodic table. So if I look this up in the periodic table, hydrogen has a mass of 1.008, chlorine has a mass of 35.45, and I get a total mass of 36.458 grams in a mole. And then I can say if I have moles of one thing and I need moles of another, I look at my equation and see that 1 mole makes 1 mole. So 1 mole of HCl makes 1 mole of H3O pluses. And that is true of all our strong acids. You can just say whatever the number of moles of the acid I have, that's the number of moles of the H plus that I have. Now I need liters of solution on the bottom. And I was given 375 milliliters. Hopefully you guys recognize by now that 375 milliliters is the same as 0.375 liters. So I'm going to put that on the bottom, 0.375 liters of solution, and now I have moles per liter. So 7.5 grams of HCl divided by 36.458 grams of HCl in a mole, multiplied by 1, divided by 1, divided by 0.375 liters of solution, and I get a concentration of 0.5486 molar acid. And then I plug that in here. Minus log of that gives me my pH. Take the log, take the negative value, and I get a pH of 0.26. It's a very acidic solution. Now I'm going to do the same thing, but now I have calcium hydroxide, which is a base. So I'm going to have an extra step in here where I have to convert from the amount of hydroxide to the amount of hydronium so that I can plug it in and find the pH, because I don't want the P, the OH, I want the P of the H. So if I look at my equation here, and you should always write this equation out, you'll see exactly why, because this is going to dissociate into calcium ions and hydroxide ions. And I get 2 hydroxide ions for every 1 calcium. So 1 mole of this makes 2 moles of that. And that's going to make a difference when I set this up here. So if I start with 4.6 grams calcium hydroxide, and 1 mole calcium hydroxide contains how many grams? I'm going to need a periodic table for this one. Here we go. If I zoom in, calcium is 40.08. So I've got 40.08 plus we have 2 oxygens and 2 hydrogens. That gives me a total molar mass of 74.096 grams. So I'm going to plug that in here. 1 mole of calcium hydroxide has 74.096 grams calcium hydroxide. So grams of calcium hydroxide cancel. And now I see that 1 mole calcium hydroxide reacts to form 2 moles hydroxide. And if I have 845 milliliters of solution, that's 0.845 liters of solution. Now I've got moles per liter of hydroxide. So that's going to give me my hydroxide concentration. So 4.6 grams calcium hydroxide divided by 74.096 grams per mole calcium hydroxide, multiplied by 2, divided by 1, then divided by 0.845 liters of solution. I get a concentration, a hydroxide ion concentration of 0.147. Okay. Now we're going to say 1 times 10 to the negative 14th divided by this value gives me my H3O plus concentration. So I'm going to store that to memory. And then 1 times 10 to the negative 14th divided by that value, 0.147. This is exactly what we just did on the previous problem. That gives me my H plus concentration, or my H3O plus concentration. And then I take the minus log of that, log negative, I find that the pH is 13. Sometimes it tells me to use 2 decimal places, and it gets mad if I don't. And sometimes it tells me to use 2 decimal places, and it gets mad if I do. That's really frustrating. I'm just going to start including all the digits that I want whenever I want it. So there. All right, next, a chemist needs to determine the concentration of a solution of nitric acid. She doesn't know what it is. She doesn't know what the concentration is, but she does know that it's nitric acid. Nitric acid is going to be just like hydrochloric acid. It's going to donate 1 hydrogen for every 1 mole of nitric acid. So if I can find the concentration of the H+, it's going to be the same as the original concentration of the HNO3. All right. So what we're going to do here then is a reaction between the acid and the base, where we then use what we know about the concentration of the base to deduce the concentration of the acid. And here's what our equation is going to look like. My HNO3 reacts with my barium hydroxide, acid plus the base, and the outer, this is a double displacement, these outer ions go together, H plus OH goes to form water. We did this way back in classifying reactions, chapter 5. Barium goes with the nitrate, I get Ba, and it's very important, NO3, 2, because the charge on nitrate is -1, and the charge on the barium is +2. And why is that important? Why do I care? Because when I balance this equation, I see I need 2 nitrates, so I'm going to need 2 HNO3s, and that gives me 2 H's and 2 OH's, so I get 2 waters. So 2 HNO3s react with only 1 barium hydroxide. That's going to be important for the equation that we've got here. So they're going to walk us through this step by step. But essentially what we're going to be doing is say, hey, if I know the concentration and I know how much of this I added, we have 0.8 molar, and I added 105 milliliters. I can use that information to calculate the number of moles of barium hydroxide, right? Because this is moles per liter. That could be liters. That gives me moles. Because I know the molar relationship, I can take moles of this and calculate how many moles of that it reacted with. And since I know the volume of the acid that I had, which was 835 milliliters, I can say if I know moles and I know volume, I can calculate original concentration in moles per liter. So that's what we're going to do. Here we're just going to do it stepwise. So they say, hey, you know that it's 0.8 molar, you know that you have 105 milliliters, you can calculate moles. This is something we did in our previous chapter on our previous test. Of course you can do that. That's easy as pie. So long as I remember that that capital M stands for moles per liter. 0.8 moles barium hydroxide in 1 liter of that solution. And I have 105 milliliters, or 0.105 liters. Your numbers are likely different than mine, so careful there. Liters cancel, and I'm left with moles. 0.8 times 0.105, and I get 0.084. Now, I'm using 0.084, then how many moles of that were present, and that's where I recognize I need a 2-to-1 ratio. So we're going to say this is 0.084 moles barium hydroxide. If I have 0.084 if I have 0.084 moles barium hydroxide, and I recognize that for every 1 mole barium hydroxide, I will react with 2 moles HNO3. Then I calculate that I had 0.168 moles HNO3. So what was the concentration if I had this many moles and this many milliliters? Concentration is moles per liter, so I take 0.168 moles of HNO3 in, I need liters, so 0.835 liters of solution. And I get 0.201 molar solution. Okay, now I don't need to do this stepwise. That's nice. I could have just done one long dimensional analysis string, but this is taking us through there step by step. All right, so balance these. It's important to balance because, as we saw, if it's a 2-to-1 ratio, that's going to affect our answer. So we better make sure that we can balance these. Okay. And that should be a subscript. Goes to form. So I just copied and pasted, and the formatting doesn't all transfer, but the rest of it does. That's easier than writing it all out myself. To balance it, let's see, I've got 1 H, 2 H's. Oh, H is all over the place. I'm not going to do that yet. 1 Br, I've got 2 Brs. So I'm going to need a 2 in front of there to balance my bromines. 1 zinc, 1 zinc. Okay. Now I have 2 oxygens, so I'm going to need 2 oxygens. And that gives me 4 hydrogens on this side, and that's 2 plus 2 is 4 hydrogens. So I feel good that that's balanced. It will take 2 HBRs to react with 1 zinc hydroxide. And if I do this one, same story. The keyboard shortcut here, by the way, is Shift _. That'll just turn that into your subscript. If you do this a lot, then it's useful to look up those keyboard shortcuts. Okay, so H3PO4 plus sodium hydroxide makes Na3PO4 plus H2O. Again, there's H's all over the place, so I'm going to wait on that. 1 phosphate, 1 phosphate, 1 sodium, 3 sodiums. Okay, so I'm going to need a 3 there. And these oxygens are already accounted for. Otherwise, I've got 3 oxygens here, so I'm going to need 3 oxygens there. It gives me 6 hydrogens. Here I've got 3 plus 3 is 6 hydrogens, so that is balanced. So this question is essentially exactly what we did right here, except that instead of taking us through it step by step, they're just going to say, let's do the whole thing top to bottom. We know how to do that. First thing we do is look at this equation. HCl plus NaOH goes to form H2O, that's the H with the OH, plus NaCl. We make sure it's balanced. I've got 1 chlorine, 1 chlorine, 1 sodium, 1 sodium, 2 hydrogens, 1 oxygen, same thing here. Okay, so it's balanced. And the nice thing about this being balanced, as we can see, is that one of these reacts with one of those to make one of those and one of those. So we have a 1-to-1 molar ratio. That's kind of nice. So if I know that I have 23.6 milliliters of a 0.125 molar solution, and I know that I've got 13 milliliters here, and I want to know what is the concentration. Then again, and you can use your roadmap for this, it'll tell you exactly what to do. You're going to use milliliters and molarity to determine number of moles. You're going to use that mole ratio to determine number of moles of this. And then moles divided by milliliters is going to give me molarity. So it looks like this. 0.125 moles of NaOH in every 1 liter of solution. That's what that capital M means. Multiplied by 0.0236 liters of that sodium hydroxide solution gives me moles of sodium hydroxide. 1 mole sodium hydroxide reacts with 1 mole of HCl. It's not always going to be 1 to 1, so you do always need to balance it and make sure that you know what that's going to be. Moles of sodium hydroxide cancel. Now I've got moles of HCl. I know the volume, 0.013 liters. And now I have moles per liter of my HCl solution. So this is not even new really to chapter 10 material. We did all this on our last exam. You guys can do molarity to molarity calculations like this, and I get a concentration of 0.227 mole. Okay, now they're giving us another reaction. This might not be something that we recognize, but they're telling us what's going on so we could follow along. Sodium oxide, Na2O, reacts with water, okay, plus water, to give, as a product, sodium hydroxide. All right, interesting. And they want the balanced equation here. We know that the sodium oxide as an ionic compound is going to be a solid, it's going to be a liquid, and that will be aqueous, dissolved in water. So here we go. Na2O plus H2O goes to form NaOH. And they want phases, so that's going to be aqueous because I'm in water. It's going to be liquid because water is a liquid. And this is going to be solid because that's an ionic compound. Oh, it's not balanced. So I have the right equation, but I didn't balance it. All right, look at this. 2 sodiums. I need 2 sodiums. And that gives me 2 oxygens, which I have, and 2 hydrogens, which I have. All right, now it's balanced. What is the pH of a solution prepared by allowing 3.25 grams of sodium oxide to react with 600 milliliters of water? There's no volume change. Then what we've got going on here is 3.25 grams of this with 600 milliliters of water, or 600 milliliters of solution. So I'm going to go from grams of sodium oxide to moles of sodium oxide, and then moles of sodium oxide to moles of sodium hydroxide. It's going to be 2 moles of sodium hydroxide. Once I've got sodium hydroxide, it's going to be the same as the hydroxide concentration. They want to know pH, so I can go from hydroxide to hydrogen and then hydrogen to pH. So let's do the first part, which is on the roadmap. And this is where we say 3.25 grams sodium oxide. And sodium is 22.99. 2 of those plus an oxygen gives me a molar mass of 61.98 grams in a mole. And then we see we get 2 moles sodium hydroxide sodium hydroxide for every 1 mole of sodium oxide. Moles of sodium oxide cancel. And recognize that 1 NaOH, and I'll write this out here, 1 NaOH dissociates into 1 Na and 1 OH. So one mole of hydroxide, and the concentration 600 milliliters, 0.6 liters. Now I have moles per liter of hydroxide. So 3.25 grams divided by 61.98 grams in a mole, multiplied by 2 moles of sodium hydroxide for every 1 mole of sodium oxide, multiplied by 1 divided by 1, and then divided by 0.6 liters gives me a hydroxide concentration of 0.175. Now I have to interface this with the equations that we've been using previously. That is to say, my H3O plus equals 1 times 10 to the negative 14th divided by my hydroxide. So I want 1 times 10 to the negative 14th divided by this value. I'm going to store that value. And then 1 times 10 to the negative 14th divided by that value, 0.174, gives me a hydrogen concentration of this, and then pH equals minus log of the H3O plus. So I take the minus log of this, take the log, take the negative of that log, and I get a pH of 13.24. Now, before I continue, it can be helpful to ask myself, do I think that I did that right before I hit submit? Recognize that this is making a basic solution because you know what a base looks like. Hydroxide is a base. So I should hope that I'd have a pH that's above 7 and probably very high because this is a very strong base. So if I made the mistake of taking, say, the minus log of this value, 0.175, thought, oh, I'm there, I'll take the log, and said, oh, my pH is 0.75, that should be a clue. Hey, that's a really acidic pH. That would not be the correct pH for a base. That might tell you that you need to look at your method again and see if you missed a step. Okay, how many milliliters of this HCl solution would be needed to neutralize this particular solution here? Well, if my OH minus concentration is 0.175, let me recall that, 0.1747876 to be specific. That's the number of moles per liter that I've got. Let's write this equation up here. We're going to have sodium hydroxide is reacting with HCl to form NaCl plus H2O. And if I balance this, hopefully you'll see 1 sodium, 1 sodium, 1 chlorine, 1 chlorine, 2 hydrogens, 1 oxygen. So it's balanced. So 1 mole of this reacts with 1 mole of that to make 1 mole of that, 1 mole of that. So that's nice. And we just calculated that I've got a 0.175 molar solution here. And they told me that it was 600 milliliters. And so now they want to know if I've got a 0.0100 molar solution of that, then how many milliliters is that going to take? So I can do that. 0.175 moles sodium hydroxide in 1 liter of solution. This is a sodium hydroxide solution. I guess that's what capital M means for molarity, is moles per liter. Multiply that by 0.6 liters of that sodium hydroxide solution. 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 0.6 That cancels. Now we'll see how many moles of sodium hydroxide I've got. 1 mole sodium hydroxide is going to react with 1 mole of HCl. So those cancel. And if this is a 0.0100 molar solution, that's 0.0100 moles of HCl in 1 liter of HCl. That gives me liters, and they wanted milliliters, so we can take that extra step. Every 1 liter has 1,000 milliliters. And we'll get milliliters. So here's where I start with number of moles per liter. Multiply that by 0.6 liters. Times by 1, divided by 1. Times by 1 liter of HCl, divided by 0.01 moles in every 1 liter of HCl. And then multiply that by 1,000 milliliters in a liter. That seems very high. I'm going to try that again. So I'm starting with this many moles per liter of sodium hydroxide. Multiply that by 0.6 liters. That gives me the number of moles of sodium hydroxide. And then I have 1 mole of HCl for every 1 mole of NaOH. And then I'm going to divide that by 0.01 moles of HCl in every liter of HCl. And then multiply that by 1,000 milliliters of HCl in a liter. And that's a lot of milliliters. 10,487. That's it. These next 3 problems are looking at the pH of acid and base buffers. Acid and base buffers are made out of solutions which have weak acids and weak bases. So what we've done so far with the pH and the reactions really works best with strong acids and bases, which is why I have you memorize which acids are strong acids and which acids are strong bases. But if I'm a weak acid or a weak base, then essentially I don't dissociate completely, I only dissociate partially. So we use the equilibrium constant to see how much we actually get in order to predict what the pH will be. So what we have here then is a buffer which contains both a weak acid and its conjugate base. So in general, we've got a weak acid, HA. It's an acid because it has an H plus to donate, which dissociates a little bit in water. That's going to attach to water to make H3O plus, and a minus. That is the conjugate base. Weak acid, conjugate base, and because it's weak, we've got equilibrium. This goes back and forth. This occurs in water, but water is a solution. Water is a solvent. It's not part of the solution necessarily. And so this is what's available for the K equation. This is just our normal equilibrium equation, which is products divided by reactants. We're going to make it fancy and call it K sub A because it's an acid dissociation constant. But really, it's just the same thing that we learned previously when we looked at equilibrium. So HA on the bottom. And then if I want to know, if I know K, if I know these other concentrations, then I can solve for H3O plus. And if I can solve for H3O plus, then I can solve for my pH. That's how that's going to work. So this is where they got, here's my equation. Here's the K expression for that equation. They dropped the water because it's the solvent and not the part of the solution. Or in other words, because it's not in the same phases as these other things. And we can solve for our H3O plus. That's just algebra, rearranging this. And then the minus log of each side gives us this equation, which can be simplified to this equation. I'm fine with just using this. And then once we solve for that, we just take the minus log of it. So we don't have to use the pKa and go through all these fancy stuff with logs. So we're going to kind of stop here and then remember that the minus log of my H3O plus is equal to the pH. Okay, so if I've got a buffer and they know what the Ka is, and I know how much of this I've got and how much of that I've got, then I can just kind of plug it all in. Now you have to be able to recognize what is A minus and what's HA, or in other words, what is my acid and what is my conjugate base. If I look at these carefully, you should be able to see this is my acid because it has the extra H. This is my base because it has lost that H and it has an extra negative charge right there. So we see we have 0.29 molar of my HA, and we have 0.90 molar of my A minus. And the Ka is 1.4 times 10 to the negative fourth. So if I rearrange for H3O plus here, I'm just going to multiply both sides by A, divide both sides by A minus, and plug in these values. So I'm going to plug in 1.4 times 10 to the negative fourth, and 0.29 molar, and 0.90 molar. So 1.4 times 10 So 1.4 times 10 to the negative fourth. Multiply that by 0.29. Divide that by 0.9. And I get an H3O plus concentration of 4.5 times 10 to the minus fifth. If I take the minus log of that, I should get the pH. So the log of that, negative of that log, I get a pH of 4.35. So this next question is conceptual, and it's asking us, what is the point of a buffer? What does it do? Why do we have it? And the idea behind buffers and the way that we use them and the way our body uses them is that you have this equilibrium between a weak acid and its conjugate base. And if I added a very strong acid, it would react with the conjugate base to form more weak acid. And if I added a very strong base, it would react with the weak acid to form more conjugate base. So it converts all strong acids and bases to weak acids and bases and maintains pH within a much more narrow range than you would get otherwise. So the purpose of the buffer system is to maintain the pH. So what does the salt of the weak acid do? That is this part, right? Whatever that weak acid is, and we say it's a salt because when we add it to solution, an AF, then it provides the F minus, and we don't really care about the cation there, but it does provide the F minus, or the conjugate base. So that's what the salt does. It provides the conjugate base. And that conjugate base neutralizes any added H3O plus, because the conjugate base plus H3O plus goes to form the original acid. If I added a strong hydroxide, bases react with acids. This is a base, so that's going to react with acid, which is my H3O plus, which makes that equilibrium shift towards the formation of more A minus here. And if I add more H3O plus, then of course that's like adding a product, and I'm going to shift back in favor of some of the reactants. So this is all just Le Chatelier's principle all over again, but looking at a system where I have a weak acid and its conjugate base in solution. So let's see what's going on here. If we have carbonic acid, tells us it reacts with water to form bicarbonate and hydronium. So carbonic acid is hydrogen carbonate. And that's going to react with water. To form bicarbonate, which is HCl3 minus. They want phases, so that's going to be aqueous. And this is aqueous. And this is a liquid. And this is aqueous. Oh, I'm sorry. They want the double arrow. So the correct equilibrium expression, the K, will be the products divided by the reactants, the same as it always has been. But it doesn't include the water because the water is liquid. So we only include the things which are in solution, aqueous. So we'll have HCO3 and H3O plus on top and H2CO3 on the bottom. And finally, what's the pH of a buffer solution containing this much of this and this much of this? If this is the Ka, we're going to just use the exact same equation. We're just going to use the exact same equation that we've got. The H3O plus is the K sub A times the HA divided by the A minus. And we're just going to replace these values with the new ones that they're giving us. The hard part here, quote unquote hard part, I don't know if it's hard, is again identifying which is my acid, which is my conjugate base. They say the Ka is 4.5 times 10 to the minus 4th. So 4.5 times 10 to the minus 4th. My HA is the acid, A minus is the conjugate base. Which is which? Well, one of these has an extra H, and one of those has an extra negative charge. Okay. This has an extra H, and that has an extra negative charge. So that tells you which one is which. The extra H is the acid, 0.14 molar. And the NO2 minus is my conjugate base. That's 0.10 molar. And then I'm going to plug that in to find the H3O plus. And then I'm going to plug the H3O plus into this equation to find the pH. So here we go. 4.5 times 10 to the negative 4th multiplied by 0.14 divided by 0.10 gives me an H3O plus concentration of 0.00063. I take then the log of that and then the negative of that log, and I get a pH of 3.2. That's it. That's how you do it. I hope this was helpful, and have a great day.